All right, so today we're going to finish up the amine chapter talking about the reactions of diazonium salts. So this is going to be very different from the reactions we've seen. But I like doing a comparison. What is this acid? Does anybody remember? It's HNO3, nitric acid. All right, we have a bunch of different acids that sound super similar. The one we're going to be looking at today is this one. It's a little bit different. This is nitrous acid. They change the suffix on here depending on the oxidation state. So if you remember going back to general chemistry, they change it to ic if you have more oxygens, us if you've got fewer oxygens. It depends on the specific situation though. All right, what happens to nitric acid if we treat it with a stronger acid such as sulfuric acid? What does it turn into? Into NO2? And if you remember, we saw this in our electrophilic aromatic substitution chapter. What's this ion called? Nitrosonium ion. Or nitronium, sorry. So the nitronium ion was the one we saw in, I believe, chapter 19. Same sort of idea occurs here, where if you treat this with a strong acid, you're going to protonate that alcohol, and that alcohol will fall off. So if that alcohol falls off as water, we would get a species that looks like this, where nitrogen can have a positive charge, and we have lone pairs on that oxygen. Why is this somewhat stable, even though nitrogen has a positive charge? Resonance, right? So we can draw out the resonance form where this lone pair can actually kick down. And so really the nitrogen-oxygen bond is really in between a double and a triple bond. Which one's going to be the major contributor? The one on the left or the right? One on, sorry, say that again? Left? Why? Well, let's think about it this way. Nitrogen has a lone pair here and here, right? Octets, right? So over here, this is actually the major contributor because this nitrogen in this form doesn't have a full octet, right? So really, when we draw out this ion, we prefer to draw this major contributor because the one on the left doesn't even have a complete octet. All right, so this is called the nitrosonium ion. And like I said, this doesn't have a complete octet, so we normally try to avoid drawing that if at all possible. Does that make sense? So let's briefly go over the mechanism for the formation of that nitrosonium ion. It's super intuitive, though. It mimics the formation of the ion we saw previously. So typically, when we do this, we buy the sodium salt. This is NaNO2. That's sodium nitrite. Oops. All right, and we saw in the first step, we treat this with a strong acid. So I'm going to use HCl here. That's the most common acid. In fact, that's the acid we used in our Azo dye lab, right? If you remember in our Azo dye lab, we used sodium nitrite and HCl. And this negative charge will steal that proton. And will make nitrous acid in solution. So normally you don't buy nitrous acid. It's just easier to grab the salt and then protonate it as you need it because it's somewhat unstable. All right, and then in step 2, we're going to protonate this one more time. So this alcohol is going to steal, whoops, forgot my L. It's going to steal a second proton.
Is that one separate step?
So we want to try to show the protonations individually. So single protonation, second protonation, because you technically have 2 different pKa values there. All right, and then we saw in the next step, that we can kick off water. In this case, the way I like showing it is to immediately show formation of that triple bond to give us our major resonance contributor, and then kick off water all in one step. So just like we saw in the electrophilic aromatic substitution chapter, these ions are really, really reactive. You have to take care when handling them, and I'll show you some reasons why a little later on. So in lab, when we were doing this reaction, we had a aniline derivative, right? So we were reacting it with another amine. So let's take a look at the reaction with amines next. All right, so like we saw just above, we had NaNO2, the sodium nitrite, and HCl. In this reaction, you're going to make a little bit of that nitrosonium ion, that nitrogen-oxygen triple bond. I didn't show it as equilibrium above, but it is a true equilibrium reaction. And then the counter anion is going to be chloride floating around in solution. And then in our next step, what we're going to do is treat this with our amine. All right, what do you think the amine's going to do? Is it going to attack the oxygen?
No, the nitrogen.
It's going to. It's going to attack the nitrogen and then kick up a a pair of electrons to that oxygen to help neutralize it. So that makes more sense. Occasionally I see students where they try to have the lone pair on the nitrogen attack the oxygen, but if you do that, then you violate the octet rule of that oxygen, so it's not going to occur. All right, so now we're ready to go. We've got a nitrogen-oxygen double bond, a nitrogen-nitrogen single bond, and then this nitrogen still has its 2 protons attached, and we have an R group attached, so that nitrogen group has a positive charge. All right, this reaction is normally done in water, so water is going to facilitate all of our proton transfers. So if you want, you can write minus H+. I'm just going to show water doing that deprotonation step. And then our conjugate acid is the hydronium ion. In the next step, what we're going to do is we're going to protonate that carbonyl, or I shouldn't even say carbonyl, that nitrogen-oxygen bond. So really this is just a proton transfer like we've gotten used to seeing. Yep, if you want. Some students just do this as plus or minus H+. I just kind of wanted to draw out all the steps so we can follow along with what's occurring here. All right, so now we've got water floating around again. Water in this next step is going to help neutralize that positive charge on the oxygen. Oxygen's not happy with that positive charge. One option would be just to rip the proton back off, but then we're just going backwards. That's not very useful. What's another option that anybody can see? So I heard somebody say take away the proton from the nitrogen, and if we do that, we can essentially cascade electrons all the way over to that oxygen. So it's kind of like dominoes falling over. So now we've got a nitrogen-nitrogen double bond. Normally the R group prefers to be trans just for steric reasons, right? So it'll orient itself on that lower side. And then we've recreated our conjugate acid. In the next step, we're going to protonate that oxygen one more time. What's the benefit of protonating that one more time? Makes it into a good leaving group. You're so used to me at this point. It's wonderful. All right. So like John said, now this is a good leaving group. right? So if it's a good leaving group, our ultimate goal is to shove it off, right? We don't really have any protons to pluck off, but it's okay. What can occur next is we can just push down this lone pair and kick off water. That results in a nitrogen-nitrogen triple bond and water as our byproduct for this reaction. What else am I missing here? Positive charge on the central nitrogen. That's a common mistake that students make. All right? Yeah?
Why did it continue proceeding forward in the reaction when you had that nitrogen-oxygen double bond? Is that not stable enough to not stay right in the center?
So you're talking about right here?
Yeah, how do you keep going?
Yeah, that's a good point. So normally with these reactions, we heat them up. Why do you think heating it up might drive this to completion? Yeah, more entropy. We're creating more moles of product. So we can push it with heat to form that nitrogen-nitrogen triple bond. But great question. In fact, I'll show you next, there are certain situations where it will stop at an intermediate that looks like this. Yep.
Depending on the stabilization of the R group, if it's like resonance stable or not, we get a lot of side possibilities of creating nitrogen gas from this.
Yes, and that's what we're going to talk about. On occasion, if that R group is just a normal alkane, this becomes crazy unstable, sometimes explosive. So we normally don't like making these with normal plain alkanes. We prefer to do them with aromatic molecules because they're a lot more stable. Good question, though. You're kind of stealing my thunder. All right. So this is called a diazonium salt. And what do you think the counter anion would be for this salt? Does anybody know? Chloride. We used HCl in the beginning, so we'd have Cl minus as a counter anion, just kind of floating around to pair up that anion and cation. These can be unstable, as Jamie was saying. No, I just want you to know that whenever you see a nitrogen-nitrogen triple bond, it's called a diazonium salt. That's really it. So a salt just means you've got a cation and anion. That's all it means. So in this case, it's charged. Yeah. It also tastes salty. Don't taste it, please. All right. Let's look at the reaction with secondary amines. I'm going to make some of you super unhappy here. Not quite. So we're going to treat NaNO2 with HCl. And we're going to make that nitrosonium ion like normal, kind of like we've been practicing. But this time we're going to use a specific amine, a secondary amine. So I'm just going to say HNR2. Yeah.
So with your other one, you had the reaction errors going the other way.
Oh, shoot.
So
Thank you, Ian. Keep me honest. There we go. So just like we saw before, hey. And H. Now we got two R groups coming off here. Just like we saw before, we have a positive charge. We've got water floating around, just like we previously saw. We can then deprotonate this, do a proton transfer. And in this case, it's just going to stop here. So getting to Leslie's point, why didn't we stop here? With secondary amines, you will stop here. This is referred to as an N-nitrosamine. This causes cancer.
What doesn't cause cancer?
Well, this is interesting though, right? So one kind of troubling thing with bacon is highly processed, right? They add a lot of nitrites to bacon to help stabilize it, make it shelf stable. Problem with that is you get this reaction going on, especially when you cook bacon. So when you cook bacon, you make some N-nitrosamine molecules in there, and those molecules have been linked to cancer. That isn't to say that if you eat bacon, you will get cancer. As most people are familiar with, the dose determines the poison, right? So if all you do is eat bacon all day, every day, you're going to have more problems than N-nitrosamine, but you'll likely get cancer too on top of it. The other big one, I'm going to get on my soapbox here. Oh my gosh. This is my bigger pet peeve than bacon, because this one's got a link that's super well studied.
You know you're attacking me.
Those be fighting words.
Yeah.
This is nornicotine. So a component in tobacco products. Tobacco products are also processed with nitrites. So if we do this, we've got a secondary amine here. We're not going to react with the nitrogen on that pyridine moiety because that's already aromatic. So instead what happens is it'll react with the nitrogen over here, and you'll get an NO double bond. So what happens is you create this in your nicotine products, and when you smoke them or consume them through chewing tobacco or whatever, this gets into your body, and this has been super well studied, and we know beyond any reasonable doubt that this causes cancer. So a lot of people get really confused on why cigarette smoke causes cancer. This is one of the main reasons that we've attributed to the direct cause of cancer there. So if you smoke, maybe consider some alternatives. That's just my soapboxing.
What's the name of that?
I guess it'd just be N-nitroso-nornicotine. Yeah. Yep.
Okay, so going back to the actual reaction.
Yeah.
So it stops because there's no like other hydrogen.
Yeah, there's no other hydrogens on nitrogen, so it's just kind of going to stop here. That, and it's somewhat resonance stabilized as is, so it's just not really going to do anything else. It just kind of hits this dead end. Yeah. All right, then we're going to go to the other fun one besides cancer. This is alkyl diazonium salts. All right, so let's say we've got an aliphatic amine. And we do this, we're going to convert that nitrogen to a nitrogen-nitrogen triple bond, right? This is the alkyl diazonium salt. What's the main problem with this? Explosions. So this bond's readily going to cleave, right? And if this cleaves, we're going to make N2 gas that will bubble out really, really quickly and uncontrollably. Classic hallmark of a bomb is something that produces gas quickly. So this is really unstable. And then the other problem is then we've made a cation that is really, really, really reactive. It'll find any sort of nucleophile or base to do whatever it wants with. You really can't control this reaction. So this is super unstable. Which means that this reaction is not practical. I know Jamie's thinking, but you can make a bomb. How is that not practical? There are better ways to make a bomb than doing this, trust me. All right. I'm not going to show you how to make a bomb. All right. Let's do aryl diazonium salts.
Then the issue is, then we'll be making bombs with these half-baked and like these.
How about we just not make bombs? That's another option.
I need something to shoot
It's
at.
a better option in my opinion. All right. I'm going to have like the FBI coming to my house tonight. All right. So the cool thing is this works really, really well for aromatic molecules. These are remarkably stable. You did this in lab, right? You had an aromatic molecule that you made into a diazonium salt. This is a super versatile intermediate and can do a bunch of cool reactions. So we'll just look at 4 unique reactions off of this. The first one involves swapping out that diazonium portion for a chlorine. Next one has a bromine. Next one, probably guess, an iodine. And then the next one, along the same lines, you can actually swap out a nitrile.
So because you have different error, we just can't use a methyl halogen.
No, we have to use a special reagent for each of these. In fact, what you have to use is a copper 1 salt. So for the first one, we're going to use copper 1 chloride. This works really well. Next one, copper 1 bromide. Next one, copper 1 iodide. And then we can use copper 1 cyanide right here. These are all called the Meyer reactions. It's really quite useful. So let's think about this. How can we make this diazonium salt? Well, what would the next intermediate be? It would be aniline, right? We'd need NH2, and then we would need NaNO2 and HCl. How could we make aniline? I was trying to get you to practice this on your last pod. Yeah, the easiest way is to go from a nitro group, and then we can do something like iron and zinc, or iron and HCl. Yep, H2PT works just as well. And then we can make this directly from benzene by using H2SO4 and HNO3. If we think about cyanobenzene in particular, we had no way of making that previously. Now we do. It's just kind of a long route to get there. And it's also a convenient way for removing the nitrogen on an aniline group and changing it into something like a halide really quickly. Does that make sense? So it is synthetically one of the more useful reactions that we see in this chapter. All right, do you want to see the mechanism for the Meyer reaction, or would you rather skip it? You don't really need it for the exam. Then no. All right. Well, if you are interested in seeing it later, it's kind of cool. It does involve some radical chemistry. It's more advanced than what our book talks about.
Like basically the bromine just acted in popping off nitrogen gas.
Yeah, so you do liberate nitrogen gas, but it goes through a radical pathway. It's pretty neat. And copper, does anybody know what preferred oxidation state copper likes to be in? 2. So copper in this case is actually acting as an electron transport. So it actually facilitates the redox reaction. So if you are curious, stop by my office hours. I might even throw it on the lecture notes later and just add it in. All right, so let's take a look at some Meyer variants. All right. So the first one is pretty straightforward. Meyer's the one I showed above with all the copper salts. So the Meyer reaction exclusively is in reference to copper chloride, bromide, iodide, or copper cyanide. These are similar, meaning they have similar types of chemistries, but don't use copper. This one's pretty neat, where you just take water and heat it up. What do you think will make? An alcohol. But you don't need copper in order for this to happen, so technically this isn't a Meyer reaction, even though it looks a lot like a Meyer reaction. The good thing with this is in chapter 19 we saw how to make phenols, and those reactions required really, really high temperatures. This occurs under normal, boiling water conditions. So this is a good alternate to nucleophilic aromatic substitution. Yeah.
Why wouldn't that N2 group
Sorry, say that again?
Like, why wouldn't it direct the alcohol to an ortho or para position?
That's a good question. In this case, the nitrogen wants to fall off very badly as a gas. That's the driving force for this. Yep. So this is a good alternate to nucleophilic aromatic substitution. With nucleophilic aromatic substitution, does anybody remember the key feature we needed? We needed a leaving group, and we needed a nitro group in the ortho or para position. This allows us to avoid the use of those nitro groups. So let's make a note. And elimination addition. What was one of the pitfalls with elimination addition? Does anybody remember? We made benzene with the triple bond. Remember that? What was the pitfall? It's unstable. That, and you often get a mixture of products. It can react on either side of the triple bond in benzene. In this case, we get pretty good regioselectivity. The alcohol will always go on that position where you had the diazonium salt. So you get a lot more control here. All right, the other cool Sandmeyer variant is this one, where we again start with a diazonium salt. And we use H3PO2. This is, it's not phosphoric acid. Phosphoric acid is H3PO4, right? So this is hypophosphoric acid. Ugh, that's a mouthful. So it's not phosphoric acid. That's the number one mistake I see students make.
Yeah, I already put the
Cool thing with this is we can convert it back to a hydrogen, which is pretty neat. So pretty powerful tool. All right, I've got a challenge for you now. All right, my challenge is I want you to make 1,3,5-tribromobenzene. How do we do that?
I would have another question actually. Could we use these reactions to produce nitrous oxide?
It'd be really silly to do that. Yeah. You can just buy that commercially.
But it's more fucking big. Look, I'm just asking because the current way I'm thinking of doing
Let's try the challenge problem.
is decomposition of ammonium nitrate, which isn't exactly safe.
Does anybody see a potential issue with getting the bromines oriented like they are? What's wrong? They're all meta to one another, right? Which means we must have had what on there originally? A withdrawing group, right? So that makes some sense, I think. So let's try that. Let's get an electron withdrawing group on there. What is a good electron withdrawing group that's easy to install in the first step? You wouldn't? All right, so at this point we can get benzene all the way to nitrobenzene. All right, you could, if you wanted, try to brominate this. Is it going to occur very quickly though? No, it won't, because it's so deactivated, right? Because it's deactivated, it's going to be a really sluggish reaction. What might be better though is convert that to an NH2. So we'll use iron and zinc or iron and HCl. Now we can brominate it because it's strongly activated, right? Is this going to be an ortho-para director or meta-director? Ortho-para. So because it's so activated, I kind of pointed to this the other day, we're going to over-brominate it. What would we do if we only wanted the para position? We would acylate that nitrogen. But in this case, we purposely want 3 nitrogens on there. or bromines, excuse me. All right, so we're getting close to our final product though. Our main trouble now though is we need to get rid of this. So first we need to convert it to a diazonium salt, right? How do we do that? NO2 and HCl. So now we've got this nitrogen-nitrogen triple bond. All right, we're almost there. What do we need to do now? H3PO2. So it's kind of a clever workaround, right? We're able to do more chemistry. In many ways, you can use this as a removable blocking or directing group, kind of similar to the sulfonation reaction we saw way back in chapter 19. This is kind of along the same line where you can use it to your advantage and then remove it when you're done. Make sense? All right, we've got enough time for our last reaction for this chapter. This one's kind of cool. This is the Azo coupling that we did. I was going to slide around our lab so that it corresponded with this lecture, but then we would have messed up our synthesis project. So I was like, we'll do it early and cover it later. I apologize. But let's think about it this way. We started out with an aniline derivative, right? So we had this, maybe some sort of R groups coming off the ring. Maybe it was di or tri substituted. Doesn't really matter as long as you've got an NH2 group there. And then we also made the ion in solution 2, right? By reacting NaNO2 and HCl. So just like we saw before, this is going to attack in. We're going to shorten this up though, and I'm just going to write plus minus H plus. And we're just going to move one of these protons from that nitrogen where? Onto the oxygen. Okay, so we've just shuttled that proton around. I'm condensing this down into one arrow pushing step. If you want to show them separately, you can, using water or whatever. All right, now we've got water floating around as our solvent. What will occur next? Yep, kind of like an elimination. We're going to grab this and cascade electrons to that oxygen to neutralize it, right? I'm going to flip that OH kind of out of the way. We know sterically it's going to want to orient itself to be further away. All right, now we've got this acid floating around. What's the next step? Protonate our alcohol, because we need to convert that to our better leaving group. Just like we saw before, this is a good leaving group. We need to shove off that leaving group, so I'm going to take this lone pair, form our triple bond, and eject off water, all in the same step. Now we have our diazonium salt. We still have chloride floating around, and we've got water as our byproduct. All right, so that was our first major reaction. I just wanted to review that so we got practice. The next step is our second aromatic partner. So if you remember way back to that Azo lab, we had two aromatic components and we linked them together. So in order to show that, I'm going to use a different color. Let's use purple, because why not? It's a royal color? I don't know, it's like a dirty husky. All right. Hey, I'm a duck. I should have used green. What is this? All right, so we got our electron donating group on there. The question is, well, why would we want an electron donating group on there? Does anybody know?
Is it gonna be like an SN2 that's gonna kick off nitrogen gas?
Kind of. It will not kick off nitrogen gas, but it's kind of like an SN2-esque type reaction. Think about it this way. Is this going to be a nucleophile or electrophile? It's going to be an electrophile. Why is it going to be an electrophile? It wants electrons, right? Which makes sense for this to be our nucleophile. And we know that nucleophiles are better when they're electron rich. Things are going to be electron rich if you have an electron donating group. All right, so now the question is, which of these carbons on the ring will act as the nucleophile? Ortho and para, right? So just like we saw in the previous chapter, if you have an electron withdrawing group, it's going to make those ortho and para positions more nucleophilic, right? All right, which one do you think is most likely to do the attack? Para, because sterically it's most accessible. So we can show this acting as our nucleophile. It'll attack that nitrogen, kick electrons over, and neutralize that positive charge. So it's not really a substitution reaction because we're not kicking anything off, but it is a nucleophile attacking an electrophile, so in that way it is similar. Oops. Excuse me. All right, this looks pretty familiar. What's this called when we have that positive charge in the ring? It's our sigma complex. All right, we know that sigma complexes aren't super stable because we've broken aromaticity, but we still have water floating around. So that water is going to help restore aromaticity to the overall system by grabbing this proton and clamping down. Thank you, Ian. And voila. Like I said in class, these molecules are really interesting as dyes. Why are they colorful? Conjugation. So these are colorful due to conjugation. The other cool thing that these are commonly used in is pH indicators. So if you've got acidic protons, maybe on your electron donating group, and under high pH conditions, you deprotonate one of those positions, it'll actually change the conjugation and therefore change the color of the overall dye. In fact, a lot of the indicator dyes that you use in classes like general chemistry when you do titrations are azo dyes or similar to azo dyes. They're pretty unique in that way. They're also commonly used in the food industry as food dyes. Some of them are a bit questionable in terms of safety, so they're trying to get away from the synthetic food dyes and going more towards natural food dyes, but there are a lot of them that they know are very, very, very safe. Pretty interesting molecules. All right, we only have a few more minutes, but I did want to end by showing you the reaction summaries for this chapter. It's the last, I would say, of the heavy-duty synthesis that we're going to be learning. The rest of the 2 chapters we'll be learning are more biochemistry. We will learn reactions, but they're not synthetically super useful. I just want you to know the mechanisms and transformations. So the first one was how to make amines from alkyl halides. We can do that by doing SN2 chemistry with sodium cyanide or sodium azide and then a reduction. We can also make amines from carboxylic acids by converting them to amides first and then doing a reduction. We said that we can do these transformations with benzene where we make nitrobenzene, convert it to aniline. This is the azide synthesis that I mentioned before. And down here we've got our Gabriel synthesis and our reductive amination. What's the big cool thing with reductive amination? Why is that so useful? Does anybody remember? We can make primary, secondary, we can make really any amine we want with reductive amination. With the Gabriel synthesis and the other ones, we're somewhat limited. So it's a lot more versatile. And then we saw we can do acylation with acid halides or anhydrides and get this acyl group to get installed right there. We also covered the Hofmann elimination where you purposely alkylate that nitrogen to a quaternary ammonium salt and then eliminate it off as a leaving group. And then today we saw the reactions with nitrous acid. Big thing is this causes cancer, so we avoid that if possible. Then we saw our Meyer reactions, which we covered today. This one is also kind of unique. I didn't hit that today. That's another variant. So you can actually put on fluorines by using HBF4. That's actually a big one right now in medicinal chemistry. For better or worse, what a lot of pharmaceutical companies are doing is they're finding that their patents are lapsing for a specific drug. And they're like, well, if I change one atom on there, I can reapply for my patent. And so then they're going out and swapping on some fluorines. And in some cases, it actually improves the efficiency of the drug and extends their patent protection. So interesting. And then these ones we saw as Meyer variants. And then we, last but not least, covered the Azo coupling. So make sure you get started on sapling sooner rather than later. I want to make sure that we have enough time to study the ACS exam. So I just want to get this off our plate before we get into carbohydrates tomorrow. Sound good? All right, and then the pod will be due tomorrow. If you want, you can use the remaining few minutes to get started.